G'day there, you're watching the Aussie Boom Guru, and today we're going to cover how to place duct supports using Dynamo automatically. So I'd like to thank Dinos for his question. He queried me this quite a while ago, and I've been working on the workflow in the background here and there, so I really appreciate that request, and I hope I've solved your problem. So I've got another video that I released previously to this one, where I actually build the Unistrut family itself that's going to support the duct. So I recommend that you watch this one first because it's a good tutorial in family creation. We build a line-based family, so essentially this is the family we're going to place using Dynamo, and we're going to set its parameters as well. So it looks a little bit like this. So essentially it's going to fix itself to the underside of the slab, which in this case is going to come from a linked model, and it's going to sit just under the duct that it supports. So the goal is a little bit like this. This is essentially what we're going to achieve today. So we're going to be able to select any element within a duct run and support the entire system. And this is the goal. So we're going to select a duct, get its system, get the ducts in that system, and then only obtain the ones of a length that we determine or more to filter out all the little sort of dicky ducts that don't matter. We're then going to determine a spacing rule and distribute our families along the runs of that duct, and then set their parameters for their height. So it's quite a complex workflow. It'll probably take a little while, but I think it'll be a valuable lesson in Dynamo for MEP users. And I know I haven't done too much MEP content yet, so hopefully this helps sort of bring more workflows to your companies. So I'm going to be using 3 custom nodes today. One is the Duct Systems All Elements and Network node from MEP Over, the Family Instance by Curve to place the line-based family from Clockwork, and then the Link Element by Raybounce from Bimorph in order to find the slab above the support. And ideally, I'm using 2.0.3, but if you use a similar version to that, it should be pretty much the same workflow. So without further ado, let's actually jump into the model. So at the moment, I'm operating in the Autodesk sample project, the RME advanced sample project, so the mechanical model, and I've linked in the structural model and positioned it so that it sits roughly on top of where it needs to be in the model. You can see at the moment I've actually just left a few supports I just placed, just to show you that this workflow will achieve this. It's not perfect, it will clash with some elements, like this isn't going to detect things like corner junctions and how to rationalize them, so there's still some work from the user required after. It won't detect things like pipes that might clash with this once they're placed, but what it will do is it will read the structural model and it will stop the support under beams and slabs at the very least, so it's still quite powerful. So I'm just going to go and delete all of these. I'll just get that out of the way. So what we'll do is we'll just open up Dynamo and we'll start a new script. So I'm just going to run in automatic mode initially, and then we'll go to manual mode once we start placing families. This way we can see our duct geometry updating live in Dynamo. So the first thing we need to do is we need to select a duct. So we're going to do select model element, and we'll just pick a duct that's on the run that we want to analyze. So now we have that model element, and we're going to get a parameter value by name because we want to find out the system that it's in. So we'll do get parameter value by name, and the parameter that you'll be looking for is called system name. You can't actually get the system itself as an element from what I've seen, but you can get the name, and then we can do a comparison to all the systems in the project. So now you can see this is a part of mechanical supply air 21. So obviously your ducts need to be in the system. That is one shortcoming of the workflow. If you're not putting your ducts into systems, workflow's not going to work. But from what I understand, this is a best practice anyway. So we're going to do a category by name, and the name we're looking for is going to be duct systems, because duct systems also exist as elements in Revit and Dynamo. And we'll get all elements of category. So if you're in a project with a lot of duct systems, it might take a little while to extract all of these systems. I think there's about 50 in this project, 45. You can see now we have all our mechanical systems. So what we're going to do now is get their name. So we're going to use the element name node and get the name of the element. And we can use this to compare where this element occurs and then extract the respective actual duct system. So you can see now we've got all these names. So we're looking for mechanical supply air 21. In this case, this is at index 18 in the list. So we're going to use index of. So in this list, where does this name occur? And you can see that we'll get the index of 18. And what we can do is combine this with a get item at index node. And from our system elements, we can get the respective element that has that name. And we should get our mechanical system that we can proceed with. And now we're going to use our first custom node. So we're going to get duct system all elements, and we want to find all elements in network from MEP over. And essentially this will give us every piece that belongs to mechanical air system 21, including the thing that we selected. So now we can actually filter these down. So what we'll do is just create a little block for this area, because this is really just the first step. So we'll just call this get system. It's a pretty big script, so it's good to sort of start blocking off these little areas in your script. What I might do is just expand this, just to give myself a bit more room in my canvas. Okay, so that's the first step. The next thing we need to do is only get the ducts in the network, because we'll have a lot of other elements in here we don't want, like flexi ducts and elbow radiuses and all sorts of things that we don't want. We just want the ducts, because they're the major elements of our run. So we're going to, in this case, get the category of all of these elements. So we're going to do get element category. And what we want to do is turn this into a string from object. This way we can compare it to the word ducts. And now we're going to check if it equals. So we've got an equals node. And we'll see we've got all these categories here at the moment, and we're looking for ducts only. And as you can guess, we're going to be using a filter by Boolean mask in order to filter down to just our ducts. A pretty common workflow on my channel if you're familiar with my videos. So from all our elements in our network, based on this mask of equals, we'll break down our elements and only proceed with the ducts in our network. So very convenient. So again, this is sort of like another little step in the workflow. So you can just call this filter to ducts. Okay, so at the moment we want to proceed with our in list, which is all of our ducts. So an interesting thing in Revit is that a lot of elements have a special behavior when you feed a location node into them. So sometimes a family might have a point at its location, but line-based elements or run-based elements will typically have a curve as their location, and ducts are one of those elements. So we're going to go element get location, and we need to get the existing element's location. And what we'll end up with is we'll end up with a whole set of lines that actually represent the run of the duct itself minus all the connectors. So we can actually proceed with this as our method to find out the spacing of our hangers. So at this point, maybe you know exactly how to solve the problem, but if you don't, stick around and I'm going to show you how we actually break these down into runs. Okay, so what we're going to do is just jump back into Dynamo, and we're going to check the length of each of these runs, because we only want to really consider the larger runs. So we don't really need to place hangers on, say, these little extensions here, because they're going to be supported off the main run anyway. We're really just concerned with these main primary runs. Okay, so at this point we need to check the curve length, and you can sort of assess pretty much what lengths you're really caring about in this scenario. So we can see we only really want in this case to deal with this one, and this one. So at this point, really it's anything over about 700 that we care about in this case. So we need to set a threshold for what we need to deal with. So we're going to use a greater than mask, and we're going to check if the curve length is greater than a number. So I'm just going to get a number slider. And we'll just set the minimum threshold at, say, 500, and the maximum to a lot, like 5,000 or something like that. And we'll just jump up in increments of 100. That way the user can say, oh, I'm only interested in increments that deal with anything over 700. So in this case, we'll get a true false list, which again, we can just use a Boolean mask on. So this is quite an important number. We'll just call this threshold for length. And you can move this off to the side because it's a pretty important control. If you like, you can put it in a little group so people can see that it's important. But what we want to do now is get some Boolean masks. So filter by Boolean mask, and we're going to filter two things. We're going to filter the locations, and what we'll do is just turn off these previews as we go. So I'll turn off this node, and then we're also going to filter our elements as well. So we're going to proceed with our ducts and their locations only if their length is greater than 700, if that makes sense. So we'll just rearrange these a little bit, clean up the script as we go. Minimum length filter. Okay, so at this point we can just proceed with the ducts from our in list, and you'll see that we'll only have 3 now. So 3 locations, 3 ducts. So what we're going to need to do now is determine the spacing of the supports along these lines based on their length. So what we'll do is just take a curve length, and we're just going to get the length of the curves that we're dealing with. We're going to build a code block at this point. So there's going to be a few variables we need. So we need a number for our maximum spacing between each support. And we'll just call this max spacing. So let's say we're going to work at a maximum spacing of 1 meter. And then as well as that, we'll also just get a number slider to inset the supports from the start and the end of the duct system, because we don't want to put them right on the end of the duct. We want to put them sort of inset so they can actually sit under the duct. So we'll do start, end, insert, and for this one we'll just say it's between 0 to 200 with an increment of 10. And we'll just say by default we want inset by 100 from either end. So I'm just going to build a code block at this point in order to determine some aspects that we need. So I'll just create a code block. So I'm going to just say that the length we're dealing with is the full length. So I'll just define a variable called flen, full length, minus the insert. And what I can do now is feed in my inset, and I can also feed in my full length, and we'll end up with a list that is that shorter length we're dealing with. What we want to do now is figure out how many spacings we need to include along our duct run. So we're going to do this length that we've created divided by max spacing, and then we're going to check the required count. So we're going to do ds core, and we're going to do math, and we're going to get the ceiling because we want to round up in the case that we end up with, say, 0 supports. And we're going to do count plus 1 for our required count. That way we always end up with at least 2 supports along our run, one at the end, one at the start, and then infill between. From there we just say that the spacing, or the distance between each support, must be the length over the required count. So in this case I need to include a couple of other variables. I think I need to do divide there, and then our max spacing. Okay, so now we can see in each one we know the spacing between each respective element. So this allows us to go and create hangers along this point. So I'm going to do another formula now, which is to determine each parameter along that curve, or each length along that curve that a spacing is going to be placed at. So I need another code block here, and all I'm going to do is create a range. So I'm going to say that I start at my inset because I'm sitting inward of the start of my curve, and then my count times my spacing, and I want the number of increments between based on my count. So essentially at this point I can say that I'm starting at my inset, and then I'm taking my count and my spacing. So in this case my count and my spacing. And what we should end up with is sublists with every single point along the run where a support needs to be placed, or a length at that point. So this part's really critical because now we're going to really use this to process the curves of the ducts based on their domain. So what we'll do here, and I'm happy for you to leave comments and ask questions about this part because it is quite complicated and it is a formula that I had to spend a bit of time determining. Feel free to just copy it if you're not that interested in it, but recommend that you spend some time thinking about these formulas. I talk about them for longer, but I think it's probably not the focus of the video. Okay, and what we can do now is actually change some of these variables, and you'll see that they'll change in respect to these parameters. So let's say our maximum spacing is 2000. So now we need less supports, but we always end up with at least 1 at the start and 1 at the end because of the way that we've processed our count. Okay, so now we're going to go and create the points along our duct to place these elements at. So the first thing we're going to do is do a curve point at segment length, because we have our segment lengths and we have our curves. So these are our segment lengths, and then our curves are back here. So we need to go and extrapolate these values. So we'll take our curves and then we'll get their points. And now you can see we've broken up our curves into these respective points. So now we know where we're going to place these elements, which is great. But now we also need to just figure out the normal at these points. So we want to find out the 90-degree direction at each of these points, because we want to create a line that is moved either side of the duct in order to place our line-based family. So we're going to do curve parameter at point to find out the domain of that point along each curve. Parameter at point. There we go. Parameter at point. So at these points on these curves, what is our parameter? And the reason we're doing that is because we want to get the normal at parameter. So now you can see we've got the parameter between 0 and 1 along the curve's domain. Now we want to get a normal at parameter. And we're going to say that the parameter is this and the curve is back here again. And now we have a vector for each of those points along that curve. So we can really quickly set up our hangers now, which is great. So we're going to create the line that represents our hanger. And in order to do this, we're going to use two geometry translation nodes. So I'm going to do geometry translate. We're going to translate by direction and distance. And we're going to be translating the points by the vectors. So in this case, we'll be moving in this direction. And we're going to move them in two different directions. So we're going to create two translate nodes. And what we're going to use to control the direction is actually the distance in this case. So I'm going to get a number slider. And this is going to be the width of the support. So let's say our minimum is 600 and our maximum is 1500. And we'll just work in increments of 100. Let's say by default we'll just do 1000 as our support width. So what I'll do here is just build a little code block, because we want to find out half of the width so we can move half in one direction, and then we want to find negative half the width so we can move in the opposite direction by half. So that overall we move to form a total of 1000 from our starting point. So we'll do x on 2 and x on negative 2. And now we should get two values that we can feed in. So we can feed in x on 2 and x on negative 2. And now you see we have points that are moved up in either direction by half of their total width. So as we increase and decrease this, you'll see that these change in size. Okay, so that's pretty easy. And then we need to just create a line by start point, end point. So we'll go by start point, end point, and there we go. So now we have the line for our support hangers, essentially. So that's really the placement method for these now determined. So that's quite straightforward. What I might do is just go back and hide some of my geometry, just because it's getting a little bit messy. So I'll hide these. I'll keep these lines here for now. I might hide the points and just leave the lines on for our placement. Cool. So if I go back into Revit, I think we should be able to see these lines as preview. Potentially, maybe not. Sometimes I find that preview lines don't show up and sometimes they do. It looks like in this case it is showing it. There they are. They're occurring along the duct run. So you can see that now we've got a method for placing. The challenge now is we need to know the height of the support and the height of the fixing to the slab above. So this bit's a little bit harder. So what I might do is just create a big group here for this. Let's group these actually. Let's call that find support curves. Okay, but what we're going to do is go back a step, and we're going to go back and figure out the levels and the heights that we're dealing with. So we're going to go all the way back here to our minimum length filter. And what we'll do is just build a code block again. And we're going to take our ducts as a variable. But actually we'll just refer to it in a formula. So we're going to say that our list of ducts is dscore list. I'm just going to flatten our list. Dot list dot flatten, and we're going to flatten our ducts list. So we'll take that, and now we should get just a list of our ducts in our run, and we'll just turn that. We'll take the first item using square bracket 0 square bracket close, just to get one duct to find out the level that we're dealing with. And what we're going to do is look for two parameter values. So we'll do get parameter value by name, and we're going to get two things. So we're going to get two parameters. One of them will be of our duct list, and one will be of the first duct. So the first parameter we're looking at is the bottom elevation of every duct in that run. So if I just go into Revit, we're looking for the bottom elevation of our duct, which is automatically determined in Revit. And then on top of that, we're going to look at the reference level as well for our first duct in our system, just to find out the level that we're placing all of our uni struts at. So we're going to just call out two parameter names here. We're going to do bottom elevation, and we're going to do reference level. Okay, so of all of our ducts, we want to get their bottom elevation. So now we have those numbers, and then we want to also get the reference level of the first duct as an element. What I'll do is just minimize this, get out of the way. And what we're going to do here is just we're going to round these, because you can see they're not very friendly numbers at the moment, so it's better that we just round them off. So we're going to apply just a standard rounding function to go to the nearest whole number. Cool, because we don't want to set up parameters with all those ugly decimal points. What we're going to do here is take our level, and we're going to get its elevation. We want to find out how high this is, and then we're going to round that as well. So we'll take a round, and because this one comes out quite unprecise as well. There you go, with 7300 is our height of our level itself. Okay, so at this point we've sort of processed our levels, so we'll just move this off and just create a group for it. Just go process levels. So now we need to go ahead, and what we're going to do is actually figure out the slab above each of our points. I believe that's probably the next best step to do. Yes, it is. So we're going to do what's called a ray bounce in order to do this. So essentially it's going to shoot off a line, and it's going to give you the first linked element that it finds. So it's quite an interesting node. It's from Bimorph nodes package. It's quite an effective node. So we're going to do element by ray bounce. Cool. So what it's asking for is it's asking for an origin of the ray, a direction, and a view. So that's pretty easy. The view is quite easy. It's just current document and active view. So we'll get current document, and we'll get active view of current document. There we go. So you would want to be in a 3D view when you run this script. That's one limitation of this, I guess. You could specify a 3D view that you're not in, but I prefer just the active view. So our direction is just going to be the Z vector. So we're going straight up. And our origin, in this case, is going to be the points of our supports. So what we need to do is just go and find those points back here. Cool. And now we should get a linked element where it hits an element. So in this case, you can see that we're actually hitting the slabs, I believe. So you can see we have a link element floor. In some cases, we actually hit a beam. So you can see here we've got a beam. So what we want to do now is find out the height of where this occurs. And luckily, we just get a point where this occurs in each case. So very straightforward. But the way that we need to process these points is quite unique. So what I'm going to do is just create another code block. And I'm just going to get the first point of each of those lists, because what happens is the first point represents the starting point, and the second point represents the clash point. So we want to get that second point. So I'm going to say that points equals ds core, and we'll just go list, and we're going to just do get item at index, and we're going to take the list of clashes at level 2, and we're going to get the index of 1 of each of those. So from our clash points, so we only get 1 point for each element rather than 2, because you'll see in each of these sublists that there's 2 points. So we want that second point. What we want to do with that point is get its Z value, find out how high it is. So we're going to say that the Z value is points dot Z, and that function will just give you the Z value, which should I've done capital P, do lowercase p. There we go. Now we can see we've got that. We want to round this as well, so we're going to do Z value rounded equals ds core math.rounds, and we'll just round off our Z values. There you go, so now they're rounded. And then the last thing we'll do is we just say, what is the fixing height? And it must be the rounded Z value minus the height of our levels. So what we need to do now is just go find that elevation of our levels and feed that in. And now you can see we have our fixing height off from the level itself. So you'll see most of the time it's the same number. You can see one exception we have is where it's hitting a beam, so it's slightly lower. So at the moment, we now have the parameter for our fixing height, which we can set into our line-based family after we place it. Because if you remember my family tutorial, there's two parameters. There's a parameter that sets the base height and then the fixing height. So we've got one of them. So we're almost there. It's pretty close. Thanks for anyone that's hung around this long. It's a pretty big workflow. So we'll just call this ray bounce for support for fixed height. Cool. And then I think we're almost there. The last thing we need to do is get the support height. So in this case, this one's quite easy because we already have the support height technically. So we know the bottom of each duct run, but what we need to do is replicate this number for each support so that we can set the parameter at the equal list size when we get to the end. So there's a few ways to do it. The way I'm going to do it is quite abstract, I guess. But what I'm going to do is count the number of supports on each duct. So from level 2, we're going to go and count the number of lines that we're dealing with so that we get 3 counts. We have 5 supports, 2 supports, and 6 respectively. And what I'm just going to do is I'm going to feed this into a list of repeated item function. But I'm going to feed it over a list combine function. And I'll show you why in a sec. So we'll get list combine. So we want to repeat the elevation. So this is our combination function. And then we're going to be feeding in our count as our amount. And for our items, we're going to be getting them from our elevation. So the way that list combine is going to work is it's going to say for each of these items, apply this function at the same level as each of these counts. So we end up with essentially a list that is matching the number of supports with the number of heights that we need. So quite an efficient little function. And then we just flatten this at the end, just to get all of the values of each of those supports respectively. Okay, so we've got our 2 lists of parameters to deal with at this point. We've got that, and we've also got offset supports. So all we need to do now is actually place the family and then set its parameters. So we're going to get our family instance by curve from Clockwork. Almost there. Family instance by curve. There we go. So what we need is the curves, and then we need the family, and we need the level. So the level's quite easy. We can just go back and extract that from our level that we got back here. That's our placement. We are going to apply this with a longest lacing as well, because we're only going to be feeding in 2 single variables for a list of variables here. I'm just going to go to manual mode as well. So now we need to get our family types, and you need to get your unistrut or your support family. In this case, I will go and find my unistrut, connect that in, and then all we need now is our curves. So if I ran this at this point, the fixing and the support height wouldn't be set. So what we need to do is actually take these families after they're placed, and we need to set 2 of their parameters as well as part of the same script. So I'll just do a set parameter by name, and we're going to take this family instance and we're going to set 2 different parameters. Okay, so the values are going to be our fixing height and our support height. So we've got our support height and we've got our fixing height. And then our 2 parameters are going to be support height and fixing height, because that's what I named them in my family. So support height, fixing height, and then I'll just quickly show you the parameters. So we're going to be setting these 2 parameters here, fixing height and support height, which essentially control the base of the unistrut support and the fixing height itself. And we're going to place the family, because it's a line-based family, so it's basically determined by a curve. So let's go. I think we're ready to press the magic button, and hopefully it all works. So I'll do a save, and I'll just minimize this window, just so you can see the placement. So let's hit the magic button, run. Cool, it worked. So you can see there that this has determined the beam, and it's placed its fixing height and its support height. So you can see here, fixing height and support height have been set. Its curve has been set based on the support, but its level has determined its placement height. And that's pretty much it. So what I might do is just quickly go to another system somewhere in this view and just run it again, just to show that the script is quite flexible. What I might do is just tab select a system, do a section box, and now we can work with this. I'll just raise my section box as well so you can see the floor above. Okay, so what I'll do is I'll just close the script and reopen it to refresh all the inputs. You could run this through Dynamo Player. I'm just going to run it through Dynamo in this case. And the only variable we actually need to change here is Duct and which system it belongs to. So I'll just do that, run, and there you go. It's done the whole system. It's found all the ducts. So pretty powerful, really flexible. So hopefully that helps other people in learning more about how to interpret mechanical elements and also how to place families based on this. So there we go. So thanks for the request, Dinos. Hopefully the workflow makes sense. So thanks for watching today. I look forward to sharing some other MEP based workflows in future. Whilst I'm not an engineer, I do have an understanding of how they work. So if you ever have requests or any feedback or comments, feel free to leave it down below. And there will be some more workflows coming in future, because I do know a lot of my fans are actually engineers as well. So thanks for watching today. I make videos 2 times a week, so if you're not already following and subscribing, feel free to do so you can stay up to date. And hopefully I'll see you in the next video. Thanks. Take care.